if you would like to play along, once you've got a copy of Isabelle, which I could make a link to that too if you need. But I'll put a link in Zooler as well. But in case you don't have Zooler installed on your laptop or whatever, I just got it on my phone, for example. And I can assure you, Isabelle doesn't run worth a damn on a phone. That's not going to work at all. Aha! Totally do that. I don't know if that's supposed to be an eraser. I'll just get that. I'll be right. That'll be fine. feel free to get more pizza and drinks and stuff if you want.
I had a small group today.
Yeah, January is usually kind of a small one because we can't schedule it very far in advance because
Yeah.
the official paperwork doesn't happen. But also, I know that there are several people who would have come who had planned on not coming because they weren't sure if ice would be done yet.
Yeah.
So that was part of it as well.
Yeah, it's still not melted in some places.
Yeah.
So it's doable right now, though. Originally, they said it was gonna be over the weekend, and then they like pushed it to Monday, Tuesday.
Well, I knew that wasn't gonna be the case, so I went to the forecast and it was like, never rose above 27.
Well, they changed it. I know, cause I had something big like scheduled on Monday to take care of, and we had to like remove it because
Oh.
when I first looked at the forecast we were scheduling, it was like, oh, it'll be back up in like the 30s and 40s on
Oh.
Monday, and then like
Oh.
it changed earlier, and we're like, oh fuck. It's like the wind chill was like 11 degrees or something on Monday.
Yeah.
That's like, yeah, we're not going.
I went out on that day, yeah,
Wow.
just to experience it.
Oh, you did?
Yeah,
Oh
I
my
just
God.
wanted to see like, how bad is this wind chill? It was cold. I didn't go too far, I just went for a walk.
I wouldn't go outside unless I was so like dressed that like I wouldn't have felt it anyway.
Right.
I ended up over at Bennu, working on this stuff.
I used to work, I'd go there every day.
Oh, Bennu? Yeah.
That's where I did my PhD, was at Bennu.
Oh, nice. The one over on,
On MLK.
Yeah, I live really close to the one on Congress.
Oh, there's another one.
Yeah,
Oh,
so it used to be Dominican Joe
Mm.
over at Congress and Riverside.
Okay.
Yeah.
There's a few of them, aren't there? There's like
No, but,
five.
yeah. They bought, so they bought Dominican Joe.
Mm.
And, also, they ended up in, opening the new one over at Highland.
Mm.
So.
This is my friend Simon.
Okay. Whatever you want. Well, I can zoom in as well, so.
So how did the competition go?
Good.
Yeah.
No,
The third
just go ahead, go
bronze
for it,
in
yeah.
the competition round got a
Sick.
cash prize.
Oh, yeah?
A what?
Cash prize.
Oh, cash prize.
2% of the cost of dinner.
2% of the cost of dinner. I love that so much.
I'm not even hungry, but it's so.
You're not
So,
even-
to Vera spread the videos, I didn't even want to share it anymore.
Burger in 2 hours.
No, that's cool. I'm glad that you did. That's awesome.
Yeah, you have to do 4 dances in a row, you have to do salsa, bachata, hustle, and tango.
That's awesome.
Great.
Where'd you go?
It was a dance competition, held at, the Marriott downtown, which is a few bucks away.
I take lessons.
Oh, yeah? What
Yeah.
kind?
Well, Jennifer Swing,
Okay.
bachata, blues. But I don't think I did it any of them. I did salsa for a while too. But
Oh, cool.
just, just try my hand at it. No, it wasn't
Yeah, I started with swing, went to the dance studio, straight out with, bachata and salsa.
That's what drew me in for the swing, actually.
I was at my first Cumbia dance social, which, that was like weird. The songs don't have well-defined endings.
Ah.
Normally at socials, the song ends, everybody finds a new part.
Yeah.
They don't do that in Cumbia.
Yeah,
It's
just
not
keep
like,
going.
the whole point of like a dance social is I don't have to like decide to end the dance, it ends automatic.
Yeah.
Why do I want that kind of pressure?
Yeah, yeah.
One time I was like, oh yeah, I think I'll get in on the next song. Any day now.
Dang.
give tax information so I can declare the price.
No.
Which I get the idea that when I declare it, okay, I'll declare the income, just so I can say, oh, and I can deduct the injury cost too.
Yeah, right.
Prize and contest?
Oh, yeah, dance competition.
Oh. Did you declare your taxes?
What about taxes?
Oh, is that what you said, they made you like declare your taxes?
Yeah, like give my tax information so they can report the cash price to the IRS. Which, okay, I get it, I believe in, declaring and paying your taxes, but it's just so I can, it's not more than I got from paying the entry fee. It's half the income.
Yeah, yeah.
Was it more than like a couple $1,000?
No.
No, then who cares?
Can you deduct the interest fee and come out ahead?
Yeah.
Taxes?
Yeah. So it's just more work.
But it's a lot of work, right?
I mean, usually if it's like $1,000 or something, the IRS doesn't care that
It was
much.
like $100.
It was what?
$100.
What?
Oh,
You don't have to report $100.
Way to get this. They think they do. They will release it and
That's
like give it
crazy.
in.
What, Silas, what did you win?
Oh, I went to a dance competition.
Oh, cool. What did you win there?
And $100 and a cheap run stop.
Now, how much was the entrance fee?
Significantly more than that.
More than that?
More than an order of magnitude.
Oh. Wait, so then you can take a loss. It's your business and you can take a
It
loss.
wouldn't be a loss, but I can, net that out.
We created a dance competition that was really a money laundering.
That must be it.
Which stories on like the crypto?
I think it's like
recording
IRS
payments.
saying, hey, you didn't report these crypto transactions, pay out me tax cheat. And it turns out it's a net loss. So it's like, oh, yeah, I overpaid my taxes, I'm so sorry.
Yeah, yeah. Huh.
Still one of them? Cool. One down.
It must be on money laundering.
I considered doing slides for tonight, but decided it's really tricky to show some of the stuff from Isabelle in Beamer. It has been my experience anyways. It will actually generate LaTeX for you. It doesn't do Beamer stuff, but you can use it to turn it into LaTeX like for your Beamer presentations. But it's difficult to look at anything actually interesting on slides. And so I think we're gonna mostly stick to the Isabelle editor. There is an Isabelle plugin that someone made for NeoVim. I met the author at a conference once. I've used it sometimes, but I don't think he would be upset with me saying that it needs a little bit more work. I don't think it's really his fault. Like the language server protocol stuff is good, but it isn't quite feature complete enough yet. And one of the things that they're missing inside of the language server protocol concepts are more advanced debugging capabilities that you would get with something like an interactive theorem prover. With the debugger, you may have like multiple areas that you're interacting with. You have like your code, you have like maybe a call stack, and then maybe you've got output from recent commands or something like that, which is a little bit more than you would have with regular language server protocol stuff, where you would just have the code and then metadata about the code. With an interactive theorem prover, you may have all of those things plus a few more items as well. you know, like current tactics being used and things like that would potentially be relevant under certain circumstances. And so there's not really clean support for that quite yet in language server protocol. I think there were a lot of people asking for weird one-off things from the language server protocol people when it first came into existence, where they were like, well, at my company, we want to have, you know, the senior engineers approve certain lines, and so we want to have like a view also that shows which lines have and haven't been approved or whatever. And like they're like, that sounds cool. That doesn't belong in like the protocol. Like, you know, that's a you thing, not the community thing. And so there had been a whole bunch of requests like that. They were just kind of used to dismissing. And then the people that, you know, working on Lean and working on Isabelle and Rock showed up and said, what about interactive theorem provers? And I'm like, oh, another like weird one-off, whatever. And then they began showing them like what the interactive theorem provers are capable of doing. And they're like, holy crap. that is way more advanced than any IDE we've got right now for some of the kinds of stuff you guys are doing. And they're like, yeah. And they're like, they're having a hard time even wrapping their heads around what all is possible with one of these tools. And so I think that kind of got them derailed a little bit. And so I think they had been firmly convinced that they were done with language server protocol until these folks showed up and started talking to them. They're like, okay, well, apparently there's more we need to do. So I don't know what the status of that kind of thing is. At least in the case of Lean, well, they've got direct access to the code base for VS Code. So, you know, that certainly contributed. So anything that they felt was missing from VS Code, you know, they have Big Daddy Microsoft, you know, push its weight around, and shit's gonna happen. But Isabelle doesn't quite have that level of clout in you know, the IDE world. But I think you know, they do have enough usefulness that it gets people looking. And so for now, people keep mostly using the this JEdit modified stuff, which seems disappointing until you remember, as we've kind of mentioned in previous meetings, that some of these interactive theorem provers end up having all kinds of languages running under the hood. You would think like, oh, normally when you think of it like a software project, it's written in like 1 or 2 programming languages. But all of these interactive theorem provers tend to be written in a whole lot of different different programming languages across a wide variety of programming language paradigms. So you're gonna have like functional programming stuff and procedural stuff and object-oriented stuff and possibly more, all in the same code base. Like, this tool is built from pieces from a bunch of different programming languages. And it's the same thing with Lean, it's the same thing with Rock. And you know, you do have the advantage on the list-based ones, that they kind of lean heavily into the list world. So the list-based theorem provers, like ACL2, like PBS, more of what they're doing is kind of leaning into what already exists in the list ecosystem. You know, I mean, even those tend to use some of the SAT solvers and SMT solvers like we did last year, like Z3, you know, and whatnot, but not quite to the same extreme that Isabelle or Lean or Rock would. So, if you're wondering, that is what we're looking at. We're looking at the Isabelle JEdit here. And so what we're gonna do is we're gonna cover this concept, which they explore extensively in this book. If anybody is interested, I can definitely recommend it. I will not say it's easy. There is a problem, which I've written on the board, which we'll talk about maybe towards the end, that I got stuck on for a very, very long time. And I still am not completely done with that problem, and that is about a third of the way through this book. Now,
What is the title of the book?
Concrete Semantics. So, by Tobias Nipkow, or Tobias, because it's German, I guess.
Yep.
Tobias, yeah. Who is one of the main people behind Isabelle, and then Gerwin Klein, who was one of his students, who has since gone on to be one of the major people behind the SEL4 project. And so Isabelle is the language, or a modified version of Isabelle, is the language that they do all of the proofs for SEL4. And so we've discussed that in a previous meeting where it was like, you know, this, Isabelle is, you know, kind of it can be used for all kinds of things, but one of the things that it is notable for being used for is this gigantic, you know, what is in some regards the single largest proof ever made, which is the entire behavior of this operating system kernel.
Do you feel like some of the momentum is moving over to things like lean?
Yeah, I mean, in many ways, yes. I like, so there was this podcast, Type Theory for All. They had an interview, I think it was on Type Theory for All, where they had an interview, maybe it was Church of Logic. It was either Type Theory for All or Church of Logic, where they had an interview with one of the authors behind, I think it was behind me, who was talking about the different languages and like trying to compare, you know, the list-based family of interactive theorem provers like PDS and ACL2, but mostly focusing on the ML-based interactive theorem provers, ML meta language, not machine learning. So like Rock, Isabelle, and Lean. And the comment came up, which I think was interesting, was that at least at the moment, it doesn't look like the language everyone is going to use for this stuff has been written yet, at least as of several years ago. Now, maybe the situation has changed. Maybe we have gotten to the point where there is enough momentum behind Lean that going forward, Lean will be kind of the way to go by default for everything. I think it's still early to say that. Certainly, there is a lot more excitement around Lean at the moment, just because it seems to have finally broken through that barrier of getting wider adoption in the mathematics world. That I think was really kind of the key missing piece that had been kind of a struggle for several of them in the past. I think for a while, Isabelle was kind of at the forefront of that. If you ever look, there's the Archive of Formal Proofs, which is a tool, a system that is inside of Isabelle, and it's a large number of proofs about all manner of things in mathematics and computer science. Very interesting stuff, all written in Isabelle, and you know, definitely worth poking around if you get a chance. But it's that was one of the largest like troves of proofs about anything in computer science or mathematics all in one place. But there was this effort in Lean 3 originally to create kind of a framework for making their own thing like that. MathLib, I think that they were calling it, and like just a framework for creating lots and lots of different mathematics related proofs in Lean, because it should be possible to do that in Lean as well. And then the transition from Lean 3 to Lean 4 happened while they were kind of still halfway through the process of building out MathLib. But they eventually switched all of the work on MathLib to Lean 4, and they converted it over. And then at some point in the last few years, some people would point to Terence Tao, one of the major mathematicians of the world, as kind of the turning point when he found some bugs in his own code using Lean that no one else had ever seen before. There may be other reasons that were contributing to that. But in a pretty recent shift, lean has become a lot more popular in the mathematics world. I've got a friend who's in the, definitely in that rung, I mean, not the top rung, but I don't know. He's definitely in
Yeah.
serious academic mathematics circles, you know, I'll say that, there's no question. And several years ago, when we were discussing this, it was like, you know, how do these tools, these formal methods tools fit into this, the interactive theorem provers? And I said, it's something that most serious mathematicians are aware of, but it's not something that they spend a whole lot of time thinking about, because it's not usually like the style, it's not what the cool kids are doing kind of thing.
Right.
And the last time I spoke with him, it seems like that had recently started to change in his world, you know. And so we'll see going forward, is this just a temporary fad? The math world goes through its own fads and stuff, but there are a lot of people who are hoping that this one kind of sticks, you know, because using mathematical proofs in the first place, I think, was at one point seen as a fad, you know, at the very beginning of that, and that has definitely changed. You know, now that is kind of the standard. If we are entering a world, we're using, you know, formal proofs in the, you know, a computer checkable system, like what is probably going to be done with an interactive theorem prover. If we're entering that world, and like permanently, that's a good thing. And so certainly I will say, on that front, although we're going to be talking about Isabelle tonight, and that's the one that I'm most familiar with, it's the one I use the most, and like I said, it's used in SCL4, so it's not going anywhere anytime soon. On the flip side, I do think we need to talk about lean at some point this year. It's just becoming really popular, definitely worth discussing. If just lean all by itself, that's an interesting topic. But I think also there has been a lot of hype in recent years about using lean with these generative AI tools. Because what's kind of interesting is, we'll play around with this here in a few minutes. You'll start to see, as you play with something like Isabelle or Rock or Lean, as you start playing around with these things, you'll realize it's kind of a weird game almost. You know, and it's the kind of thing that generative AI would be able to play around with to some extent. But unlike most of the things that you would use with generative AI, when you finish something in here, you're done, and you know you're done. Which is very, very different from almost everything else that generative AI would be able to do and is worth doing. There's plenty of things it would be able to do, but who cares? But this is an area that they might be capable of doing this. We'll show you here in a minute that maybe they're not batting 1,000 at that moment, but they might eventually be to some extent capable of doing this. There are people actively working on trying to do that. There's a lot of excitement around that in the world now, because unlike the generative AI stuff on its own, if it generates crap all day long and it turns out that's all that it generates, well then how valuable is it in the first place? On the other hand, if generative AI is able to make this even a little bit easier, that is a very big deal.
Well, every time I turn around on LinkedIn, there's someone that says, oh yeah, you know, some Olympiad question that generative AI managed to solve.
That's usually what they mean, is they're using that along with something like Lean. And actually one of the people who's kind of at the forefront of this kind of thing is here at UT. And so I might try to see if we can get him to come be a guest speaker if he's ever in town.
Who was that?
Chudri. So he's working with Google DeepMind on that.
Oh, Swart?
Yeah.
Swart, oh, okay, yeah, here's my post I realized it.
Oh, okay, yeah, yes.
When I was right, yeah, okay.
Yeah.
Yeah, someone I know is actually involved in something called CS Live, which is like the computer science
Yes.
version of MathLive. So they want to prove all the theorems about undergraduate level data structures,
Yeah.
things like that.
Yeah, absolutely.
Which I'm guessing that the SEL guys probably did all that, and in Isabelle?
So they've done some amount of that stuff, yeah. Like if you look at the archive of formal proofs, the AFP, there's a lot of that stuff is in there. I think it turns out what SEL4 needs is kind of unique. And so it is more likely that they would copy as a starting point something from one of those rather than use it as a library. And I think that's one of the takeaways. I don't think we're gonna get that far tonight, but one of the takeaways that you would get from interacting with these a lot is it's really interesting. It's kind of a cool game almost, but as you get too many things, too many like dependencies or whatever, too many libraries inside of there, not only does the tools start to bog down with just the sheer breadth and weight of everything happening, you actually, at some point, you start getting into contradictions and stuff, because just the way that the needs of one part of the code and the needs of another part of the code are so different. You know, we're used to thinking about, like, in an object-oriented programming language or something where you're doing encapsulation, possibly to cover like proprietary details about how something works, or just to keep turf wars or whatever it's going to be. When you're dealing with some of these formal mechanisms and the machine check proofs and everything, you may actually need that level of isolation in order for truth to be which is an uncomfortable situation that requires discussing with mathematical philosophers and what is the implications of that fact. But that's a kind of neither. That's a separate matter. I think that's one of the things that's important to keep in mind. A weird detail we don't normally think about. The assumptions you need in order to create a proof aren't the same things that you need for the theorem itself to be true. Okay? So maybe in order to be able to construct a proof of something, you have to add additional axioms that the proof on its, like the theorem on its own did not need these other things.
Okay.
That, again, gets into weird areas of mathematical philosophy that I am not qualified to talk about. That is,
But you just have to strike once and we'll remember you forever.
Yeah.
Some goalpost shouldn't be moved.
yeah, that's right.
So you're scratching at it.
Yeah. So, anyways, that's where we're at with that kind of stuff. So, let's get into this. So with concrete semantics, what are we even talking about? So if you've ever written a compiler or dealt with programming language design at that level, you can think of, there are two major aspects to thinking about a language like that. You've got the syntax and the semantics. These are kind of a way that you can break down concepts inside the language. Syntax is, what is the structure of a valid sentence? And so there are all kinds of rules about what words are acceptable, what order you have to put them in. In order to be able to convey meaning, you have to have some amount of structure to the language itself, or else without that structure, the thing can just fall apart. And largely speaking, compilers are mostly concerned with syntax. Now there would be some debate on that, because clearly the compiler is taking one language and turning it into some other language. And so in some sense, the meaning of that language has to be imbued from one language into another. So you have to translate the meaning. So you have to have some notion of what the meaning of the language is. But a lot of times when you're dealing with just a compiler, it depends on how you're doing it, but if you're dealing with like Lex and Yak or something like that, Lex would entirely be a matter of syntax, and Yak is going to be halfway syntax, halfway semantics. But you're not necessarily having to get into a formal definition of a semantic for your programming language. It's also worth pointing out that in many cases, when you're dealing with semantics inside of a compiler, you're able to kind of kick the can to the other compiler You know, so if you're using lexn, yeah, generally what that is doing is it's turning it's making a compiler of whatever language you've got, and probably making it into a C compiler most of the time. So what happens is inside of there, you're translating your programming language, whatever it looks like, into code written in C that's generated based off of how your programming language is set up. That will then be turned by the C compiler into assembly and whatever you know, CPU that you're dealing with. So that way you don't have to, as the person making, you know, programming language, a high-level programming language, now have to be intimately familiar with every detail of every single CPU architecture out there in the whole world. Because the people at GCC or the people at, you know, making the, you know, whatever compiler you want to use, Clang, you know, have taken care of that kind of stuff for you. So in a sense, you're not necessarily, you're kind of, I don't want to say cheating, you're just avoiding the question, largely speaking. There's some aspects of semantic definitions that you've got, and some that you're not. So how can we talk about these semantic definitions? Because that's the thing, is when we want to get into something really complicated, as we have discussed with formal methods, they are, you know, systems and tools for dealing with, you know, complex systems which we want to make proofs about. And so we're already talking about these like really specific behaviors of programming languages. You're not getting a whole lot more complicated than that in practice. And so there's a couple of different ways that you can approach this. One of the ways that we are going to focus on here is with concrete semantics. And so that is saying all the way down to the behavior of a simple, like a Turing machine. How is the system behaving? And so in our particular examples, we're basically going to be taking the question of how does this programming language that we're going to go construct here in a second, how does it behave in terms of a particular system? And our magical system that we're going to be running on is kind of like an associative array from string names to integers. This is a really simple programming language. The only thing that exists are names of variables, it's just a string, and then integers. And at any point in time, which we call a state, it's just like this dictionary. It's this associative array, it's a lookup table, a hash map, whatever you want to call it. This state that we're going to be defining our programming language's behavior in terms of is going to be just look up the variable and it gives us an integer. And that is the only thing this thing will do. Now, if you wanted to model a more realistic programming language of some kind inside of a more realistic computer, now you would have to have a more sophisticated notion of what is your state. It could be that this might actually be sufficient for most computers. If you think about it, you kind of twist it a little bit. It's worth remembering that in C, the only primitive data structures you have, essentially, are integers, floats, and then you've got your structural ones, so like your struct or your union or something like that. So it's just integers, floats, oh, and then arrays, so sequential access, and that's it. And that's C. And so since almost, as we just described, almost every other programming language practically is defined in terms of the behavior of C. Well, there you go. That's enough apparently for almost every programming language out there. It's just the primitives inside of C, and that's integers, floats, which sometimes you could even do away with, and then just structural behavior, and then arrays, you know, sequential access inside of memory. So we're not that far off, but we're at least for the moment, you're going to have to grant us that somehow magically our computer All it has is string names for variables and integer values at specific points in time. You're just gonna have to accept this. If we can accept this, then we can move on.
Sorry, there's strings inside the array. You said the state is the integer it pulls.
The state is the point in time snapshot of that array.
Okay, so it can be a string. It doesn't have to be.
So the key is a string, the value is an integer.
Oh, I see. Okay.
That's it. So it's just a point in time value of that associative array. So you think of it like a JSON dictionary.
Yeah, so
it's like a JSON object. You got a whole bunch of keys, and your keys can be strings. Maybe the string happens to be made of digits, but they are strings. They're not numbers. And then inside of there, all of the values for all of the properties in your JSON object, all of them are integers. That's it. And we haven't said if they were signed or unsigned, so we'll allow them to be signed for our programming language. But it turns out it doesn't really matter that much. But as it just so happens, the way Isabelle is doing it, it's giving you a signed one here. So it doesn't add that much complexity. So that is how we are going to be defining our system. Just for today, again, like if you were doing a different programming language, you might want to start differently. That's how this one's going to be. So now we're moving on from there. Another weird thing to think about, it turns out you can think of a programming language as being made up of several different programming languages. So, okay, well, what do I mean? Well, I mean, obviously, again, when we're talking about C, you've got C versus the C preprocessor. Okay, yeah, we know those are different programming languages. And then you might have regular expressions, which is kind of programming language into itself. Okay, yeah, this is also the case. Okay, cool. But I mean something more fundamental, that like your mathematics, like integers and stuff. That's another kind of programming language. And so in this case, we're going to have something which we call an arithmetic expression, which is a really, really, really simple language. And all it is either a numerical integer constant, so just a numerical constant, a variable name. So it's just the string. It's just the value that's going to be at whatever is at that location in the state. That's all that one is. We aren't even assigning it yet. All it is literally the string, which is referring to a value that would be somewhere in the state. And then,
sorry, so the state itself is the string, or is the string inclusive of the integer also?
The state is the entire associative array of all the strings to the integer values at a point in time.
The array of having to tell you variable names.
Yeah.
Yeah. So it's the whole thing.
It's the whole thing. Yeah.
Okay.
But it doesn't change. States the state doesn't change. They're two different states. If there's any change, you would transform one state into a different state. So you've got this arithmetic language, if you will. It's not a programming language, but it's a kind of language. It's just numeric, integer, literals, variable names, which don't even have the state associated with it. It's just the string that we're going to later talk about possibly relating to the state. And then plus, which is just saying that we want to add two other things, which are arithmetic expressions. So it could be it could be we're doing plus and then two integers. It could be plus and then two variables. It could be plus with another plus inside of it, and then one of them is an integer. However complicated you want to make this, we're building up this notion of an arithmetic expression only from integer constants, the names of variables, and plus. That's it. Now, recursive forever. It could be an infinitely long arithmetic expression, but it only involves those three things.
And in this case, what does the bar stand for?
Oh, this is just the syntax. So in
Basically means one.
yeah, yeah. In a sense, it means or, but it means or in a particular concept. We are saying that this data type arithmetic expression is either in something called a num, which is left undefined, which is associated with it an integer, or something called var, which we leave undefined, but it has something associated with it, we happen to know as a string from the previous slide, or previous part, is we're importing the state thing up here. And then you've got plus, which is taking two of these arithmetic expressions, so it's a recursive definition.
So you need those as tags, so you know which one you're referring to.
Exactly,
Yeah.
and that's just about dealing with the structure, that's the only reason why we have it there. So, now, this weird construction, it doesn't have any meaning, in a sense, this is the syntax of the arithmetic expression, but it is not the semantics. So semantics emerges from all the other pieces we build around it. So in this case, we have something which we're gonna call arithval, so it's the value of an arithmetic expression. And what that is it's taking, it's a, you know, in these, a common functional programming paradigm is that instead of describing how you create something, you describe whether something matches or not. So saying something is a valid arithmetic value if it matches one of these rules. So you could put arbitrary stuff in there, but if it doesn't match one of the rules, then it's going to say that's not an arithmetic value. But if it does match one of these rules, then it's going to say, oh, okay, that is a valid concept of an arithmetic value. So in this case, if we want the arithmetic value of a number, one of these primitives up here, and s, so just some arbitrary state, then what will come out the other side is equals. In this case, the entire statement can be, you can swap out those two, is essentially what we're saying here, once we get there. Just the interior integer value thing. So it doesn't matter what the state was. If you're saying, what's the arithmetic value of 3 given this state? And it's like, well, I don't even care what the state is, it's 3. You just told me it was 3. So that is how we establish the arithmetic value of a particular number. Okay, now what about if you give us a variable? Give us a variable name. I'm not happy with this, but this is how Isabelle does this by default. I actually tried doing some amount of syntax sugar for some other stuff later, so we don't have to deal with this kind of stuff as much. I think an easier way to think about this would be, it's more like S open bracket V close bracket. That was
confusing, because like you have that notation, you just have S in front of it, and it's like Lisp or something, it's a function application.
Yes, and that's what it is. It's because it's a functional programming language. And so in this particular case, it turns out that these states are actually mapping strings to variables, and that is the map. The map is a function that does that. And so in this case, it is the function which takes as its argument a variable name and outputs as its results an integer. Okay, and so you're applying
That is the
S
state
to V.
is a function that turns a variable.
But another way to think about that and that's just because of the nature of functional programming language. That's just how a functional programming language thinks about these things. Equivalently, you can think of this in this particular case, just like square brackets. It's just S square brackets V. That it turns out that actually does mean the same thing at a conceptual level. Making proofs about that is left to the as an exercise to the reader, but they do mean the same thing in this context. So now the interesting one, the definition of plus. What does it mean for plus to have a value? Okay, so now it means that we are evaluating at the state S both the first item in the plus and the second item in the plus. So that means that we're not doing short circuit evaluation. This is point in time evaluation. So that means that evaluating A isn't modifying S. If you're used to C or something, which you can do modifying state as you're evaluating items inside of there.
So I'm modifying the state, just using state to know what the values of A and B are.
And B are, yeah, at a point in time, exactly. And that's all that's doing. So, okay, we've given some context of like, okay, what does it mean for this arithmetic expression to have a value? Okay, let's get down here. Constant simplification. And so, again, with the number and the variables, those don't look like it's doing anything. But what's interesting down here is this +1, where if you are trying to add two numbers we already know are integer constants, then we don't need to carry that concept of the plus around. We're just like, we'll evaluate it immediately. That's basically what this is saying. We're going to add A and B right then, and that is the value. Otherwise, we do have to keep that plus, like language construct carrying around with us. So in a sense, you run this arith constant simplification on some value of this arithmetic expression type. And if there are just constant integers that can be added together, it just does those immediately. It's a thing that your compiler does without even mentioning it, but we have to call this out explicitly here.
It's just a roundabout way of saying anytime you have a plus where both arguments are integers, you can
immediately.
reduce it.
Yeah. Yeah.
Otherwise, you have to leave the variables alone, including anything added to the variable.
So now we get to the very first thing that's kind of interesting. So far, it's like, okay, well, we're just talking about the behavior of this programming language. What does this Isabelle shit have anything to do with this so far? We haven't seen any proofs or anything. Now we're gonna get to our first proof. It's a really simple one, but you can probably see why it would be important that it is true. Remember that arithmetic value, is just trying to figure out what does it mean for this arithmetic thing for some particular state. What is it supposed to mean? Oh,
I know, they want you to pay attention.
And so it turns out we want to show that using this constant simplification thing doesn't change the value. So we want to say that if you take the arithmetic value of this constant compression of A, then it means the same thing as the arithmetic value of A. So in a sense, that this constant simplification thing isn't breaking anything about the way that A works. Just because you added like a whole bunch of integers in a row, that we didn't do it wrong, essentially, is what this thing is saying. And so we want a mathematical proof that this is true. And one of the things that's kind of cool about these theorem provers is most of the time, you don't have to tell them shit. They just do it for you. And so in this case, we're just like, we just give it some really, really basic instructions. We're like, okay, here is this statement, which we think is a valuable thing to know for sure. And we want to use induction on A, so that means all the different possible arithmetic types. We're going to use this concept of mathematical induction, where you start with the base types and then all the recursive definitions you prove as a consequence of the previous one or whatever. And then from there, a variety of really basic logic simplification things that it knows about, pointing out, giving it an extra hint that it might want to split apart the different concepts inside of the arithmetic definition up here. That is it. So it's kind of a basic thing. And one of the things that's cool that Isabelle gives you, which is like what some of the other ones give you. If I can find my damn mouse. There, okay. Oh. State. So here's one of the things that you get in these interactive theorem provers that you don't have in other programming languages. Over here on the left-hand side, it is saying, again, what is it we're trying to prove? And if we go down here to the output, scroll down a little bit. I'm going to tell it to go figure it out on its own. So in Isabelle, that's called trying. There's also a sledgehammer, which does this slightly different behavior. Try basically throws the kitchen sink of all kinds of tricks. It tries all kinds, solve direct, quick check, try zero, sledgehammer, a whole bunch of different tricks.
You said apply and then you gave it, it looks like you said use solving it. I don't know what the argument is to, actually, I guess you said.
Yeah, okay, apparently didn't figure that one out, so okay, let's see. Apply, induction, A. Okay. So what the apply induction A did was it figured out, oh, okay, this definition of A, something about our proof of this statement, arithmetic value, that the constant simplification thing didn't collapse anything. This, you know, when we start up here at the beginning, it doesn't know anything. It's just like, okay, that's, somehow we need to know this thing is true. If we just tell it, hey, here's a hint, why don't you try induction on A? Because A, again, it had a recursive definition, so induction is kind of the trick that you would need to do something like that. And as soon as we told it that, it's saying, oh, okay, if we're using induction on A, then the mathematical proof that that thing was true looks like this. We have three different parts we need to prove. We got to prove that running this numerical constant compression thing on, if A is literally just an integer, that works. Well, we already know that works because we talked about that. So, okay. Now we have to know that it works if it's just a variable name. And as we saw, the variable name doesn't get modified by that compression thing. So it's fine too. The only thing that actually changes is how the plus gets evaluated. But it's not that far off of what we're doing. And the trick is, as you see, because we're doing induction, I think we briefly mentioned induction in the past. Basically what you're doing is you assume all of the things, you know, you prove that it's true about all the things which are baseline true about the recursive definition. And then you prove parts of the definition that are recursive. So like if you're dealing with the integers, you've got, or natural numbers. So 0, 1, 2, 3, 4, off to infinity. So those are the natural numbers. You start with some number, 0 or 1 or whatever you want to start with. And then every number which comes after that is some other number plus 1. And so that is the inductive definition of natural numbers. Is that you start with something and then it's everything that comes afterwards. It's a common mathematical, you can think of it as like a design pattern for dealing with math proofs. In the same way that like when you're dealing with programming, you may have these, like all the different design patterns, like the factory pattern or the singleton pattern or all that kind of stuff for solving a particular engineering problem. And maybe there's different patterns you could use which would all be valid. But for a particular problem, one of them is a better choice. Induction is one of these things in mathematics. A lot of times it's a really handy thing to use. And when we're dealing with programming language definitions that involve recursive stuff, it's almost always what we go with. So in this case, because we've already proved it's possible by the parts of the definition that don't require recursion, now we get to assume that all the previous parts of the recursion are true, and then from there prove that the next part is also true. And that's what it's saying. And so now if we try this try again, maybe it'll work now. Yeah, there it is. Try.
What did try do that wasn't doing before?
Okay, so what did you do? Okay. Okay. So up here, if we run try is going to try all kinds of tricks that it knows about. Solve direct, quick check, try zero, sledgehammer. And there are more. Let's see, what else is it done? Are those the only ones it's tried? And nitpick, okay. And none of those was enough. Only in case of emergencies should you try this other one. Try _hard.
Alright.
sometimes they get confused. Try hard thinks it's not true, it's like, okay, well, it is true.
Like, for a minute, what is it doing there as for state?
Lambda x dot minus 1. Yeah, it's saying, what if everything is -1 by default? And you gave it a 0. And it's like, what? It got confused. So that's why try doesn't always work, but sometimes it works. So you got this, we gave it the hint, apply induction A. So that gave it the hint, oh, okay, well, we need to break it down like this. But the funny thing is, now when we do try, almost immediately it figures out, oh, the only thing that was left is simp. So simplification solves these. And so now, what that means is you can replace the try with apply simp. It solved one of them, it didn't solve all of them.
Wait, what? So you already explained applying the simp versus induction. I need to just put.
This first one, just apply induction. It's telling the theorem prover, hey, automatically go try this induction trick. Okay? Try is like easy mode. It's like guess and tell me what you figured out. And so in this case, try is like, oh hey, apply simp is a thing that you could just type in and it will magically make it work. But sometimes try is wrong, like here. So you see we've got 3 things we need to prove. So if we do apply simp, well, it got rid of one of them. But the other,
so the fact that it's not there means that it's proven.
yeah, that's right.
Yeah, I was wondering, like, what is the syntax for knowing that something is
On the
solved?
right-hand side.
Yeah, on the right hand side here, because we've got the state thing open,
Yeah.
this is showing us what is left to do. This is kind of our to-do
You want
list.
it to be.
Yeah, we want to prove these things are true somehow. And so, we'll get to that in a second. So it's like, well, crap. It said apply simp. That made it sound like everything was going to be done. So let's do try again. Apply simp again, which is frustrating, right? Except we still have one more thing to do.
So nothing seems to get rid of that.
So then we did try, no, it was just doing one at a time. That's what's happening here. These apply simps only run one at a time. But now, I think that's why we have this arithmetic expression split. It's because I think this one won't be quite so clean. So the first apply simp, it just went and solved the first part of the problem.
I know, but I don't know.
And as soon as it was done with that, it's like, okay, I'm done, and it's not going to do anything else. Which is like, damn it.
Well, what is the dot? That dot split isn't defined.
Ah, yes. We'll get to that in a second. So one other thing that's worth pointing out, auto will keep trying to apply simp over and over again until it's done. So that's part of the reason why this one just did it. Another way to do that is to put a plus sign. Well, it also applied simp inside of there, and so now we have seen the thing that we were trying to apply. So if we did, I'll show you. Apply simp. Okay, so that now it's that one. We got the first 2 items off of there. So if you see up here, we got 3 things we got to prove. This first apply simp got rid of the first one. Second apply simp got rid of the second one. One more doesn't solve the problem, but it does modify what we're doing. So it figured some things out about this thing.
I gotta take off right now.
Oh, you got that? Okay, yeah, see it.
Alright.
So, but what we can do is try this.
Why is it indented like 1 extra character each?
That is a good question. I find it frustrating. There's other people who like it that way.
Oh, really?
It is indicating which sub goal was being operated on. That is the default. indentation behavior.
Ah, so it's like one space per sub-goal?
Yeah, I don't like that shit at all.
That is really odd.
But that's what it does by default.
Huh.
So, yeah.
Wait, can you explain it again?
Yeah, it does it one level of indentation based off of which sub-goal it's working on from back to forward. So this is two spaces in, because this is solving the third from the last sub-goal. When we did new line after that apply sim, the thing figured that out, and so it added the 2 spaces in. I have fun. What's really confusing is when you're doing a whole bunch of different things, and then you start to see them like, oh, this one's 5 in. Oh, this one's 3 in. Oh, this one's 4 in. It just like moves them back and forth, because as you're trying different tactics, it's applying to different ones in particular orders. I hate that. But what we can do here,
Yeah. You was the mom.
oh yeah. What? That should have worked. There we go. And that's what you want to see. No sub-goals. That is, when you have a really big proof in Isabelle and you see that, that is party time. As you go out drinking, that is man, is that a nice thing to see on a problem. From experience, when you've been dealing with the same problem in Isabelle for, 8, 9, 10 months, and then suddenly you see that shit, oh man, that is awesome stuff. So what's happening here is, in a sense, because this auto, as I mentioned, also includes a whole bunch of simps as many times as you want. We can actually get rid of those two, because that apply auto would have kept doing all the simps for us, and that's why, that would be enough. So then you could do done after that, and then we're done. However, there is another syntax thing which I was doing here, which is by putting a comma, you can actually combine 2 successive ones in a row. So now,
Here's the original one you
that does the whole thing in one line.
I was gonna say, but the one I downloaded, it already had, so
Yeah.
you would kind of read it right here.
That's right. Okay. That is, this apply stuff, is how the big boys and girls working on this stuff usually just throw things in there. Because if you're really comfortable with Isabelle and you know what you're doing, you know what you have to do to build that up. I still like doing ISAR, which is what I'm going to show you here in a minute, which is a different way of doing these things. So we've also got this way to simplify the pluses. We are also doing a proof that this plus stuff isn't changing anything. This is a different way of compressing the data and everything. So I'm going to gloss past this, the rest of this. Go over to another sub-programming language we've got, which is Booleans. So Boolean language is a little more complicated. You've got Boolean constants. You've got not a Boolean constant. You've got and 2 Boolean constants. And you have less than 2 arithmetic constants. And this less than means that the first arithmetic expression is strictly less than the second arithmetic expression when you evaluate them. Which is not something you will know unless you have state, or unless they happen to both be integers or something. So, and this is giving us the Boolean value in the same way that we had the arithmetic value before. So it's doing all this. Notice that we don't have an or in here. We just have and not. And and we don't have a greater than, we don't have an equal to, we have this less.
Even not less than.
So if you wanted to create an or, you could make an or by combining some of these. If you wanted to have a greater than, you could do it by swapping the order of these things. If you wanted to have an equal, you could do, you know, a combination of nots, ors, and ands, and less thans, and you would be able to
We're gonna
give
have the
yourself.
absolute minimal primitives for this.
Exactly. So, now why, like, that seems annoying. Why are we bothering to do that? Well, you'll see here in a second. So, now we're on to the meat of this talk. The programming language itself, the top level one. Okay, so the only things we have in our programming language are the magical keyword skip, which does nothing, something called an assignment, which takes a variable name and an arithmetic expression, okay? Something called a conditional branch, which takes a Boolean expression and 2 more commands. Okay, remember this is a recursive definition, so these commands were off here. Sequence also, it just takes 2 commands. Okay, and this conditional loop, which takes a Boolean expression and 1 command. Okay. Now, to make it a little bit less awful to deal with some of this crap, I'm not going to go over this too much. I'm just going to tell you what this does. This is making some syntax sugar that makes it not make your eyes bleed. As we do all the rest of this stuff from experience. Inside that same code base, if you go look inside of chapter 7, the CH7 at the top level, that is more of what the real one from the book looks like. And I'm not doing the syntax sugar there, and so it's kind of a weird, gross looking thing. In this case, I'm doing a bunch of syntax sugar to make it a little bit less awful to deal with this crap. I'm giving us magical constants true and false. So instead of having to deal with b constants crap all the time, you just have a true or you just have a false, and that's it. As weird as that syntax was for applying a variable, so you've got the state, and then space, and then the variable name, which is actually treating the state as a function, which takes a variable name argument and returns an integer. It's kind of weird.
But this is a question. Does it break everything you open to imp.py, imp.chys?
No.
It'll know which imp I'm talking about from the side menu.
Based off of the context of where the other file you're looking at is from. I don't want to go too much into. There is a way to explicitly state what the manifest structure should look like. There's like a manifest style file for Isabelle, which will explicitly tell you where things should be included. By default, it will include from a very small set of the standard library from main. So if you import main, otherwise anything else you import, it assumes it's from the same folder you're currently in.
Okay.
And so if you have an imp.thy from this folder and you open another one from a different folder, the one, unless you have a really complicated manifest file going on or something, it's only going to be dealing with the one from the same folder. So you can open them both in there and do stuff with them if you want. It'll be okay. So as weird as the lookup stuff is for state, declaring a new state is more complicated. So I had made my own syntax for declaring a new state. And come on, where's the damn mouse? Where are you? There. Okay. And the new syntax, is it there? Well, it's basically, okay, this is about the variable names. The variable names will start to look a little bit more like shell script variables. So we'll get to that in a second. And then the state ones, is that down here at the bottom? Yeah, state ones are down here. So it's going to be the literal phrase state replacing variable name with value. So like in this case, if we have a state S and we're changing the variable V to have the new, the variable X to have the new value V, that would be like, make a copy of S. Now inside of our copy of S, assign, do S open square brackets, X close square brackets equals V. That's kind of what you can think about what is happening here. It is making a duplicate of S where the only thing that has changed is the value of the variable X is now V. That's what this weird syntax crap is doing. So, like I said, I don't want to dig too much into this because this is just about trying to make the Isabelle code not be so hard to read. Now let's get, but here's the programming language, the first code snippet from our programming language. We've got a program which we're going to call sum210. We're not dealing with variables, like input variables to a function. Like we're not dealing with that yet. That would be a more complicated thing to deal with. This is just a program. It doesn't take any variables, it just does it. And so in this case, sum is starting off with 0. And then I is also starting off with 0. And now we are checking while, in the curly braces thing, I, so think of it like a shell script variable. So the value of I is less than 11, do sum is the value of sum plus I, value of I. And then you are also adding 1 to it. So in a sense, this function is going to add up the first 10 numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's the first 11 numbers. And then the result at the end of this while with sum is going to have the answer. So you kind of, we're not trying to super deep explore this language yet, but do you understand what that program is doing here? Thank you.
And you can think of like the dollar sign is like value of quotations.
Yeah, kind of. And then the only time you don't use the dollar sign is when you're assigning to it inside the colon equals thing. So now we're going to get into the main thing we're talking about today. Let's close this state over here because we're not going to need it yet. And let's close the output.
So that program doesn't run, the sum to 10, like, it's just an example.
That was just the string for now. Yeah, it's not running there.
Oh, okay.
It could, but we're not that far yet.
Okay.
That is just the string that represents the code.
And why does it give you that error, the ambiguous input?
Oh, that's a long story.
You don't have to go into it.
That's a long story. That has to do with parse tree stuff. There's only one. If you look down inside the guts of that error, it says that only one of them was actually valid. And so it turns out that the tricks that we are using to make the syntactic sugar. Oh, if you need, let me get you here.
Really good.
This is the code that we're dealing with. Yeah. Okay. So that is just the that has to do with how we define the syntactic sugar and everything. That's why it's complaining about the way that it is. Only one of the possible parsings is a valid expression inside the programming language, and so it's okay. If there are two possible valid versions of that thing, it would have complained. But it's like there's all kinds of like loose end weird because of how we did the syntactic sugar. That's all it is.
And sorry if I missed it, but did you define the syntax just in terms of data types?
Yeah. So so
in other words, the program here is just an expression of that.
Of this type. This is the programming language. Yeah. So it's something that is recursively defined by anything that matches this. That's the program. So that is the syntax of the programming language. And then the syntactic sugar is what gives us like turning those things into the actual while do's, all that kind of stuff. So now let's go look at, this is the definition of the meaning of this programming language we had just described. Okay. So the big step semantic describes, so there's possible different concrete semantics. There's the big step semantic, there's also a small step semantic. You might have a different kind of semantic. Big step semantic is what we would call a concrete semantic definition that says what is going to be true about the program when the entire program is done running. Okay? When you started the program, you run the whole program through to completion. Now what is the final state? Okay? So what's happening is we are adding some syntax to help, specifically this weird C, S tilde to T. I use the like squiggly arrow thing. On the front of this book, they're showing this. This is the thing that they usually use for big step semantic in programming language books and such. So when you're talking about big step semantics, it's the big double arrow most of the time. In the context of me explaining this stuff, I found that we were using that double arrow, which in Isabelle also means implies, and it also means a bunch of other stuff. I was like, that is too confusing. Anytime you see the squiggly arrow T, that is what we're talking about. We're just talking about squiggly arrow T. And that's actually okay. Like in the computer science world, that's okay. Like you can do that. So CS, squiggly arrow to T, means that running the program C, so C is the program, it's like the structure. We might represent it inside a string here in a little while. You'll see what we're talking about. With the state S, running the whole program until it finishes gives you the state T. That is what the big step semantic is defining. It's basically saying what has happened when the whole program is done to the state. So you don't know what the state, you could have any number of possible states at the beginning. We aren't saying anything. We're not putting any imposition about what is the state of the system before we start. And that's common when we're dealing with things like concrete semantics. It's difficult to reason about with different kinds of semantic definitions if you aren't making all kinds of assumptions about the sanity of the state when you start the program. But that is one of the things that you can get by taking kind of a formal approach to a concrete semantic, is that you can say, no, we are not making any imposition at all on the state. The state could be literally anything, and this is how it will change. Now, maybe some states would give us bad results, but that fact should be represented in the state transition that we're going to be demonstrating. Like, if that's going to happen depending on the state, that's one of the things that should pop up in our definition. And again, as we mentioned earlier, these are declarative, not procedural, so it's not saying how does the state transition, it's just saying this sequence of events matches a possible valid trace, is what we would call it, trace of the program through the possible states. You know, this represents a valid execution or not. We're not saying how we're constructing them. We're just saying this does or does not represent a valid transition. Okay. So now we've got this inductive big step. So we're going to define our big step definition, big step semantic definition, using this induction concept. And what it takes is a command and state combo, and then it leads to a particular state, and either that sequence is true or false. So in a sense, it's just this big step thing is a thing which tells us whether this command run from this state results in the next state or not. That's all it's going to do. And so what this inductive definition here is, it's going to show us all the ones where it is true. So we're giving true definitions. So here we go. Let's go through how does the programming language behave. So we'll start with this skip S. So if you have the program, which is just the command skip, and there's nothing else, when you're done running that program, nothing has changed about the state. You start with state S, you end with state S. So pretty straightforward. The program did nothing to the state. But,
Yeah, no one.
yeah, no one. Yeah. So now we've got the next one, which is a rather interesting one. But as I told you, we've got this weird syntax thing that I'm doing here to make it less awful. If you have the program for the variable x, assign it the value of a, and you're running that with the initial state s, okay, then that will change. Running that program from that state changes the state of the whole thing when you're done running that program. So again, the program is only that one thing. There's no loops, there's no ifs. It's only that. That's the whole program right there. If that's the whole program, all it is doing is it's taking a copy of that S, like duplicated S, but inside of our duplicated copy of S, we're replacing X with that arithmetic expression A evaluated for S. So we actually go find the value. When we perform this assignment, we go and evaluate the arithmetic expression right then. And then that is what we put into B. Because remember, this state can't have other variable names on the other side. It only has integers. So we have to have this thing give us an integer. And so that's why we have to find the value right then. Okay. A little weird to think about, but next we're going to start to see a little bit more, you're going to get a little more flavor for how these semantics start to work most of the time. Sequence. So by default, your programming language doesn't necessarily have more than one command in it. It could just be one. But you can fix that by having this recursive definition that allows you to keep adding more commands to it. In our case, it's this double semicolon thing. So our assignment was this double colon equals. That was one of the things that we set up in our syntactic sugar crack in the previous one that we kind of glossed over. In this case, our syntactic sugar to give us a sequence is this double semicolon. So A double semicolon B takes us from S to T. Okay, but how do we know what T is? We didn't define T. Well, we did up here on the previous line. The only way we know that this statement is true, that this A followed by B, starting from state S, leads us to T, is if there is some other state X, which we haven't defined anywhere. We're just like, state, I don't know what that state is. It's out there in the ether. You start from state S, you run the command A, and somehow this magical state X poofs into existence. I don't know what that state is, but there it is. But if we also happen to know that if we run the command B from whatever the hell that state X was, whatever that magical state that popped into existence, if it happens to be the same one that running AS leads to, if that running B from that state leads to T, then we know that A followed by B starting from state S leads to state T. So in a sense, we have to already establish ahead of time how does B running from state X behave. But that's the nice thing is we can use whatever the hell X we want there. If we know that we can show both of these things are true, now poof, we get this other thing, which is kind of it's a result of being able to know that. Okay. It gets a little more tricky when you're dealing with like branching behavior. In this case, you're actually going to have multiple definitions for the possible ways it can behave. So in this case, we're going to do like an if statement. If the statement is true, so in this case, we have if G, then A, else B, and we've just got phi on the end. just to make it easier for the syntax parser to deal with it. Okay. So if G is true, so that's what this first thing is saying. If when we evaluate G at the state S, that is true, and we have this running the command A from state S leads to T, then down here, that means that the entire if statement run from state S leads to T. And since we don't care what B was, again, evaluating G is not changing the state, then the entire if statement, if we already know that G is true, the entire if statement is the same as if we were just running the one A command. Similarly for B, when we happen to know that G is not true, we don't even care what A is. If we know that G is not true when it's evaluated from the state S, then that's enough to know that the entire if statement is the same as if you ran B from S. Now we get into the weird ones. So if we know that the value for our while loop, you have while G do C odd. So this do odd thing, kind of an old school way of ending a while loop. If we know that G is false, then I don't even care what C was because the loop wasn't going to run. So it's basically the same thing as running skip. S doesn't even get modified. If you hit that while loop and you know somehow magically, nah, the thing was false from the beginning. Well, it doesn't matter. We didn't change the state. Next one gets tricky. So if we're with the loop true. Okay, so again, while G do C odd, but now we know that G is true. So we know that G is true. We're going to again talk about some kind of a magical intermediate state X, which we haven't defined anywhere else. It's just poof into the ether somehow. If you run C, one iteration of the loop from the state S, and it gets you to X, and somehow the entire loop run with that state X gets you to state T, then we know that the entire loop gets you to T. Again, this is not a very efficient way of calculating these things. All we're trying to establish, is it possible to do this? You know, we're not trying to calculate these things. It's declarative. We're saying that this is a thing which is true. And so you kind of see what we're talking about here. Basically what's happening here is we're checking to see if G is true, we're going to peel one of the iterations of the while loop off of the front and then evaluate it again. So in a sense, we are now recursively deciding how the state changes over time when you run this while loop. So we are doing recursion all these other places, we may as well do it here too. So it's a little bit of a weird conceptual leap, but essentially what we're saying is we are recursively defining the entire change of that program, that while loop, is being the same thing as recursively peeling one if off the front, one loop iteration off the front over and over and over again until somehow we know that it ends. And that is the big step semantic for this programming language. Okay. So that's a lot. Now we've got, well, what can you do with the big step semantic? Well, one of the things that's interesting to do with the big step semantic, are two programs the same thing? So remember earlier when I said, well, if we have like that while loop and somehow we know that it is false. So we're using this big tilde thing. So here's an example. I'm going to have while false do C, whatever C is, odd. And I I've got skip. And I can tell you that because of how we define that big step semantic, what we're saying here is that these two things are tilde. That means that they're kind of a notion of equals to each other. If for all initial states S and all final states T, running program A from state S gives you T, and running B from state S gives you T. So that it doesn't matter what starting states and ending states you're in. If you run the two programs from the same starting state, they get to the same ending state no matter what. If you can prove that's true, then you know that they are equivalent. And yeah.
And out of your enough for these three limits.
Yeah, and these three limits, these are like the standard equivalence limits. So this is reflection.
Mm-hmm.
So that was kind of obvious that a program is big step equivalent to itself. If A is big step equivalent to B, B is big step equivalent to A, which isn't surprising since, you know, there's nothing that's one side or the other. The interesting one here is we also have transitive equality. So if A is big step equivalent to B and B is big step equivalent to C, then we know that A step is big step equivalent to C. So if one of those, if these two things are easier to prove than this one, then it's enough to prove these two things, and then we get the third one. And so, yeah, this is an example. We know that nothing that you could possibly do from this program will ever change the state in the same way that this one won't. But there's other things which we would know are equivalent. Okay. How about this one? Okay. X is 9001, immediately followed by, no if statements, no nothing, just immediately followed by X is 42. Okay? Actually, we don't even need those parentheses, do we? No. Okay? That thing is equivalent to just X is 42. Because there's no possible state you could start with on this program that anything else is changing. No other variable is changing. The only thing that's changing is X. And it doesn't matter what X was before, it's going to be 42 when you're done. And it's the same thing with this. And so these two programs are the same. Now, to be clear, if we change that to like Y, now these two programs are not the same, okay? Because now we're talking about something to do with Y, which we weren't talking about here, and so we can come up with states where they're not the same state, and that would be easy. That would mean any state where this wasn't already true for this one, they would be different. Now, it's worth pointing out, if somehow, we knew from some previous part of the program that Y is : equals 9001, then that whole program with that extra redundant piece here would be fine. Yeah. But yeah, if they're both X, those things are equal. Okay. There's another interesting one. Come on. Good. Okay. Another interesting one here. If you had how about this one? While true, do C odd. Okay. What does the big step semantics say about this program? Now, we're not talking about necessarily big step equivalence either. We're talking about what does the big step semantics say?
Could you put the semantics back up?
Yeah, I'll do it. So get down here. This is the relevant one. We know that G is true. So while G, S, so that's true, and CS leads to X, okay? C is running in this case, and so the state is possibly changing. While G do C odd X goes to T. Okay, so we're recursively saying what's the state change. So what do we know about this from the big step?
Well, I think the previous, in the assumption, doesn't go to T, right? There is no T.
Yeah, does it run forever or something?
Yeah, it's an infinite loop.
Oh, okay.
And so that's the trick. The way the big step semantic is defined, it requires us to know that the thing already terminates. Or else we can't say what the big step semantic does. So, this is a program for which there is no big step semantic. In a sense, from the perspective of the big step semantic, this program is undefined. It doesn't have meaning. Now,
So is it equivalent to skip?
no, it's like the opposite of skip,
Okay, okay.
because it means that the state could potentially change forever.
Uh-huh.
You know, I think, I mean, it's not entirely true because there is a way that you could do it. Because remember, as I said, that induction is like it's like a design pattern. Sometimes you could use a different design pattern. So what other way could we know this? And actually, in this case, you wouldn't be able to. From the definition of the big step semantic, the way we have defined it, you actually can't solve this. But you could slightly relax this a little bit and you would be able to get an answer. And the way that would be is if somehow something about this program led you, about the nature of C, let you know that nothing was going to change. So right now, even if C was skip, with our definition of big step semantic, it would be undefined. But we could slightly adjust the definition of big step semantic, which would allow us to have skip inside of C, and then it would be defined at that point. So you kind of see what we're saying there. If somehow you could prove that the state wasn't changing, or basically if there's anything you could say for certain, like a priori about the state change, the total state change of any number of this command running, and then you would be able to potentially modify the big step semantic to say that that's also valid. But right now, the way it's written, you wouldn't be able to. It would just not be how it would do it. So, we're out of time, unfortunately. But I'll show, no, before, I'm going to show you. This is how I usually do proofs in Isabelle, using ISAR. And so in this case, those two proofs that we were talking about doing, here is the, here's my damn mouse. Okay. Okay. First one here, there was that one where we're trying to show, X is equal to 9,000 or V is equal to 9001 followed by V is equal to 42. And we're saying that that is big step equivalent to the program that's just 42. And so here's how you would do something like that. So this is saying, what is the proof that we need to make? So it's for all S and T for all T. Assigning V. So this is what our programming language looks like without all the syntactic sugar, if you're curious. Actually, it's keeping this double semicolons for some reason. The rest of it's getting rid of the syntactic sugar. So it's saying, do we know that these two are the same? Okay. And so one of the ways we can do that is, so we've got two for eaches, and for each S, for each T. So we get here to the end of here. Now we see how the state is changed. This intro, all I, if I. So all I is saying, okay, we're going to allow just specifying some arbitrary value of S and T. We're just telling the proof assistant that's the type of proof we're going to do. But we're also telling it, also, because this is like this tilde, if you remember that's that big step equivalence we were saying, it's an if and only if, it was a double-sided arrow thing. Well, the standard way to do that in the mathematics world is this, you prove one implies the other one, and then separately you do the other one implies the first one. And so we're telling the proof assistant, we want to do a type of proof that involves introducing these for all S's and for all T's, and also that we want to do the one direction and then the other direction. So we start off getting some arbitrary value for S and T. It's like, I don't know what the S and T are, but I'm just saying, okay, they exist, and I'm going to use them. And now we want to assume that this is the program, and that somehow it takes S to T. You know, that's how we know that we can show these two things are equivalent, is if we assume that this is the program, and it starts in S and it ends in state T, that means it behaves the same way as if just V is 42 starts with S and ends in T. So we want to prove that a piece of the time. And so this ISAR, instead of doing all these applies and stuff like that, it looks a little bit more like what you might see in a math proof, like in a math class or something. And so I'm saying, I'm assuming this is true. Now I want to say, I think there is some value called X for which these two statements are true. You know, this V going to 9001, and then S leads to X, and then V saying that that's 42, starting with X leads to T. And I think those things are true because of these reasons. So I think I can get this X. I think you can give me this X because somehow we know it's true because of this.
Just a question, should be this roundabout. I mean, we just kind of proved it very directly by saying, hey, both of them ended this state. We could see that, so.
It's kind of the point of formal proving though, isn't it?
Yeah, I mean,
as cohesive as possible to get roundabout.
You gotta make sure
The proof should itself be simple.
So you could certainly, so this particular, at least this direction for sure, there is a shorter way to do it, just using the applies and stuff. I was preferring to do it more of a math approach, where we take it step by step and say why we know it's true. Under the hood, if you did apply or something, it's doing something like this, just automatically under the hood. So you're right, you can just use the automation, just say, you know, apply auto or something. That would just,
We're trying to fully prove something out.
No, but I mean, it's, the proof we kind of did informally over here is pretty simple. Like, all we have to prove is that both end at state 42.
yeah, but it's a math proof, so we have to be very, very particular about how we do it, especially formal proof. So in this case, we're saying that somehow this X exists, and now I am saying that X is S, where we swap out that V value, whatever V was before, with 9001. Since we don't know anything else about S, we're just saying it's exactly the same thing, except that one is swapped out. And now we're saying that T is X when we swap whatever value was at V with 42. And so to your point down here, yeah, now, here's the trick, by simplification, and this T equals X replacing V with 42, that X we replace with this. So now T equals S replacing V with 9001, that now replacing V with 42, is what it says over there. And so, to your point, yes, now we can collapse that and say now T is equal to S replacing V with 42, because now we know that replacing V with 9001 followed immediately by replacing V with 42. That is true, that reduces to just V is replaced with 42, based off of actually another proof that they have in Isabelle, and that's the trick with these formal languages like this is you can't just, oh, it seems easy, like, wouldn't it be, like, nah, you have to spell it all out. Now, that's the thing. These interactive theorem provers have a giant pile of things which are useful for collapsing things like that. And in this case, Isabelle does too. Isabelle will recognize, oh, okay, we're changing the state twice. We only care about the second one because it's throwing away whatever's happening in the first one. And so now from this, that is enough to show that S gets us to S replacing B with 42, which means that that's the same thing as T, and now that means we're done with our proof.
Replacing is substitution, right?
Yeah, this replacing blank with whatever, that was part of the syntactic sugar thing that I did. That is just a easier way for us to represent what the Isabelle code is saying, which is exactly what you're saying. It's just.
Oh, you defined that. Oh, okay, I thought it was part of the Isabelle syntax.
Yeah, this replacing blank with blank is my syntax, because the actual Isabelle syntax is, that's where they use square brackets.
Oh.
And it's just like, no, thank you, no, thank you.
2 minutes square brackets.
Yeah. It is. I've always found Isabelle's syntax for that to be particularly confusing. It doesn't look like anything from any other programming language. So now, okay, so now we've established that the 9001-42, that means that the same transition happens if you only have just the assignment to 42. Now we have to go the opposite direction. Oh, but you see here, sorry. Sorry is an Isabelle thing. That means that the, oh shit, I can't get the proof to work yet. Just pretend like it's true and we'll move on. Which is useful when you're dealing with like a really, really big proof. And like maybe like a dozen people are working on the same proof or something. And you're just like, oops, I screwed something up inside of one interior part. I don't want to throw everybody else off in the entire rest of the project. So when your proof is not like totally good until you've gotten rid of all of your sorries. But putting sorries in place kind of allows you to like move on, and we'll come back to this later. So in this case, I had to do that because something about our syntactic sugar is really tripping up Isabelle from recognizing that T means the same shit. We didn't do anything weird here. And so I actually have to do like, I don't know, I glossed past that too, but inside of our syntactic sugar thing, I actually added a whole bunch of dumb little properties about the syntactic sugar itself in order to get Isabelle to recognize, like, don't worry about this crap, like, unfold it. I'm just doing this to read, dude. Like, this doesn't have meaning. I'm doing it so it doesn't look awful when I'm working it. And it's just, I'm like pulling these things out one at a time, like, and my impression is that is a very common pattern among people who do Isabelle or Lean or whatever on a regular basis. Is they're always like fiddling with like, God damn it, like the matchers are not working right. Now I have to adjust stuff. I have to massage the definitions. I have to massage the loading order to make sure that we don't run out of memory too early in the proof. You know, it's like it doesn't change whether it's true or not. It's just that the thing trying to evaluate it might run out of memory and crash before you're done if you don't do it in a particular order or something.
So if it's just for pedagogical purposes, if you just stuck with the terms, would that have been, I mean,
yes,
so bad?
if we had just done it like this style,
Right.
yeah, it would work just fine.
Right.
Yeah.
Yeah, I'm just wondering, that wouldn't have been so bad, for the purposes of some example.
Yeah, well, and that's the thing, if you inside of that same code base, I was pointing you to this FMUG folder. There's also a chapter 7 folder, and that is using the ones from the books, and those are working. And they're working because they don't have all the syntactic sugar I even added to try to make it less awful to work with them. Because the number of times I ran into typos, because I'm like, wait, which assignment? How many parentheses do I have to put here? Like, this X is different from the other X. So, okay, I'll add another, like, single quote. And so I get like an X with like 5 single posts because it's like nested so many layers deep, and I need to make sure that it is different from the other X's that were different because I'm referring. Oh man. That kind of crap happens a lot. So, unless you're doing a lot more of the applies and stuff, and you can, but again, I kind of like. I'm more convinced that this is true sometimes. So, and certainly for more complicated stuff, this is really justified because this is a lot better about showing subtle problems or whatever. Another one down here, this infinite loop one, we're going to show by contradiction. So we've got this proof. Somehow, you know, we say that it is not the case that that while true do skip odd s gets the t. So even skip, we're saying, doesn't work inside this infinite while loop. And so we're going to assume that it is true, and then from that we're going to show contradiction. So we're working a piece at a time. So okay, this extracting C makes it easier for the thing to recognize that the induction is supposed to work. But then we get down here, and my try is broken for reasons I don't know. Like that one should have figured it out, but like everything else worked. But once you get to the loop truth, then it just got totally bogged down. Like So, but if you look at the other chapter 7 stuff, you can see a lot more of the ISAR stuff, and that's the way I like dealing with these things in ISAR instead of dealing with them with the applies.
What is ISAR standing for?
I feel like it probably has some. It's not all caps. It's capital ISAR usually. I don't know where the name comes from. But yeah, that it's just the name for this in Isabelle. This style of proof. It's like a different syntax. So when you type proof and then you start doing stuff, and it kind of looks like a math proof more like. That's called ISAR. They've got other things like things that you compare with Isabelle, like Hall. There's other mechanisms you could add with Isabelle. So Isabelle is kind of like the framework. Hall is usually like the collection of all the stuff that we normally care about with the math and everything. It's kind of like
the libraries.
Yeah. Because a lot of those I think came from. So Hall is also the name of another theorem prover mechanism. But I think they both get their name from a particular effort to formalize a lot of proofs and stuff using higher order logic. So it's like a particular style. So
You can mix and match things if you start with this ISAR thing and then you decide you want to use sledgehammer or you want to.
Yes. Well, and in fact, right here I'm using proof.
Oh yeah.
Yeah. A lot of those things you can use, and you can mix. You can do an apply and stuff inside of here, or vice versa. I think they usually say it's better to avoid that if you can. Most of the time, whatever it is you would have done with an apply, you could have done with ISAR. Now that said, if it's going to be like an extra 300 lines of ISAR, or you could have done one apply, and the thing that the apply is doing kind of matches more of the way that humans think, you may be in a situation where it just makes sense to put an apply there. But Gerwin Klein, actually on his blog, he has like a series of advice about when you should and should not be using applies with ISAR, or only use applies, or only use ISAR, or whatever. So. Well, thanks for coming out.
Thank you.
We've got more stickers. Yeah.
The parking.
Oh, and parking passes, I would strongly recommend, if you park here, you want one of these, because boy, is it expensive to park here without this.
Where am I bike?
Oh, you're in right? Yeah, that's the way to go.
Yeah, me too.
I walked and I only got 2 hours of sleep last night, so there you go.
So I think next month, we may end up doing, we might end up doing, the current hours. Yeah. Oh, you want to race?
No, well, I can't erase.
That's fine.
Might as well.
Anything I
I
can
mean, we got a lot more napkins back there, so. Next month we'll probably do Curry Howard, because we're thinking about it, but we need to do lean at some point. And if we do lean sooner, then maybe eventually we'll end up doing lean with the AI tools, which will be interesting.
Yeah.
We might get big turnout when we do that. When I go and post in a public forum that, hey, we're gonna be doing AI stuff that doesn't break out loud on the right part of LinkedIn or on Twitter. Well, I don't know if I'm Twitter these days, but like, yeah, and the right part of the Capital Factory Slack, like, I bet we're gonna get a lot of people show up.
So AIT actually ran like a Luma like calendar. So
Yeah.
if you partner with them, then like you might have a lot of people.
Yeah, that's.
There was a meetup yesterday. I think they had like 200 people RSVP. Like it was like so busy, it was ridiculous.
Yeah, and I mentioned to Elijah about that earlier. So we might, when we do that one, I mean, hopefully we can get like Professor Trudering or whatever to come and give that one, because that would be better, I think, if he'd be willing to. I need to go see if I can go get some of those professors to come be guest speakers.
Are you taking any donations for the pizza?
No, but that's appreciated though. Just me.
Anything I can do to help clean up, Charlie?
Yeah, let's get, if we can get like the plates and the peppers and stuff in there, yeah.
Yep.
And if anybody wants to take home whatever pizza's left, it's appreciated. Just keep it for next time. We'll yeah. I appreciate it.
Yeah, I mean, you know, pizza's not cheap.
Yeah.
There you go.
I'm on the bike, so I can't take any pizza with me, so it's a good thing, I think I've had
Yeah,
enough.
right. Combine those two, take them.
Sure.
Sounds good.
Okay. Do we check the boxes, or does someone come in and grab them?
No, right before we leave, we'll end up putting them on top of the trash. Okay.
You want to put the plates and stuff inside this bag, Charlie?
Just bring them up here, because I'm gonna put them in this other bag. I appreciate it.
Yeah.
How much meat one is left? Is it just a couple slices?
No, it's a pretty big.
I think it's half of it.
More than half.
Yeah.
Yeah. How's everything going, Constantine?
Pretty good, pretty good. What about you?
Pretty good. Yeah. No complaints. Yeah.
Are you using AI nowadays?
Am I using AI? I mean, I feel like I've used AI for a long time. 'Cause, I was doing like GitHub Copilot before, like ChatGPT got big, and yeah.
I found like I was looking for like some stuff, and I found that like Wikipedia it now has like 6 million articles, so it basically has like the same, almost the same number as Wikipedia, and basically
well,
like
suspiciously the same number as Wikipedia.
but like I think they started because like like I was looking like into the history of it, right? So they started like in October or November, but like it didn't used to have like most of the computer stuff it didn't use to cover. So it just covered like the popular things, right? But I think like roughly, it seems like roughly like 2 weeks ago, they basically added like almost every article. There was like a sub article on Wikipedia. They added it as an article.
Yes.
And it's like so extensive. And like I just looked at like we're talking about Wikipedia. And I looked at like some of the articles that like I wrote, and like I know that like I wrote that they're basically kind of like sub articles, right? So it's they're basically kind of like sub articles on Wikipedia, right?
Yes.
And in Grok, they're completely extensive. Like it followed like all the podcasts that were listed on Wikipedia that weren't like kind of like described at all, right? And like summarized the whole thing, like found like a whole bunch of stuff that like it takes a lot of reading to find and stuff like that. It was amazing. It's pretty amazing.
That's pretty cool. Huh.
So basically, if you find some sort of any sort of like tag topic on Wikipedia, right? Especially if it's like some sort of not like a mainstream tag topic, then you go by the same name on like Wikipedia, and it's very extensive.
Yeah, yeah.
And I think like it shows like the time that it was created, and it was created like all 2 weeks ago. So I checked like a whole bunch of topics, and it was all created 2 weeks ago. And it's already like in the top like 20 results in Google search. So I imagine that like in a few months, people will not be reading like Wikipedia anymore.
That would be crazy.
Something falling in?
One thing they're
Something
kind of.
fall?
Oh, what happened?
Like bits of pizza or something.
But one thing is that they don't like their references. They don't do like the proper reference kind of
Are
thing.
you gonna put that in there? And I was like, how are you gonna do this with so many bags?
Well, I on the way over it was quite annoying, but
Yeah.
this time it's not too bad.
Okay. Okay, just 2 bags then.
Yeah. That's not bad.
Yeah.
Now what to do with that other
What did you
pizza?
want?
I don't know about that.
Yeah, I don't eat meat.
Oh, okay.
You are welcome to take that one if you want.
Are you taking it though?
I'm not.
Okay, I'll take it.
Thank you, Charlie.
Yep. Well, thanks for coming out.
Can I help you to your car or anything?
Oh, I didn't drive my walk. Actually, I took a lift because I had 3 bags. And now I only have 2 bags, and so no big deal. This is easy. Okay. 3 bags was not easy. 3 bags in a hurry.
Mm-hmm. But rush is not fun.
You want any?
I'll get one more. So now
Yeah. Veggie stuff too.
There we go. No.
Sure?
Yeah. That's it for me. You are welcome to the rest.
Okay, thanks.
Yeah, thank you. We all are. Oh. Only other change we got to make is this.
It's kind of like so cold here today.
Huh. Yeah.
Yeah.
Top floor and everything.
On mine?
Yeah.
But it's actually like outside. It's not cold outside for some reason. I was actually kind of surprised. Like I walked here like when it was freezing, and like I didn't feel cold actually.
I mean, straight news.
There's that one. There's the one. The rest of them look good enough. Good enough. Good enough. Okay. Yeah, we're good. Oh, we're out by 9. Here we go.
Go. Thanks for